good evening to everyone, and I like to thank all those organizing members and the volunteers of this FDP uh, based on the renewables, which is the today is the trend or need of the society. So today I will discuss about mainly about the AI-based grid connected systems, right? So here, what are the issues is there and how we can use the AI for what purpose. So I will discuss mainly about these things in detail. So and also very thank to the Rajivjis for giving me an option to interact with this audience. So I think this will be very valuable for you as well as for me also. So in this discussion, AI-based grid connected mode.
Dr.
So
Nishant, I'm just interrupting you. Meanwhile, I'm sorry for that. Can we record your lectures?
yeah,
Because
sure,
it
sure,
is
sure, definitely. Yes, you can
okay. Okay, thank you very much.
okay. So so in this AI-based grid connected mode, mainly why AI is important here. So actually, the grid connected mode solar integration is nothing new here, right? So we have the converters, and then we can through the converter we can proceed. So not a big deal here. But now our expectation is much more with respect to the traditional power generation side, right? So today we want extra more. More means we also want to system information, system resiliency, or system coordination, coordinated behaviors. All these things we want with the system. Means system is not only as a generation. Here the system is also share with the different generators, communicate with the different generators, and then react accordingly. So this is our expectation. Means day by day, once the technology is enhancing, so our expectation is also increasing in that manner. So that's why here AI is important. Okay, so I will start from the beginnings, then again I will come on the actual problem, right? So here in this entire system, I will consider this type of system. Means the we will I am considering one solar panel, and then few local loads, and then connect with the grid. Very simple household solar panel, or we can say the rooftop solar panels type of system I have considered here, right? So I have not considered here battery, right? So here I have assumed that this grid is behave like a sink and source for us. Means whenever we have extra power, then we will feed those power in the grid, and whenever the power is not sufficient, for example in the night time, then we will take from the grid. Means for us the grid is sink and source here. So this is the our consideration here, and everything is based on that. Okay, so if you will go for the classification and all, then definitely this system is classified in the different manners based on the your you can say the uses. For example, a grid connected mode, as well as we can use these things for in a standalone mode. Means when the grid is not there, then system will behave like a standalone. Also, grid side, this classification is also in the two parts, single phase and three phase, right? According to that, we can share the power, or we can say the exchange the power. This is the network configuration side mainly, you can say that. Next is your another topology level, or the you can say the connection level or converter level mainly. I will say this is single stage and two stage. What is these stages? I will discuss that during the system. Okay, so if you will think about the classification, further classification based on the connections, so you will see the two type of connections you will find here: string inverter based connection and micro inverter based, right? So string inverter based connections means your all the panels will connect in series and parallel according to your choice for the current and voltage, and then after that all the panel output terminals will attach with a single inverter. That is your string inverter connections. Or you can say the micro inverter sides, means a group of panels, not single one, a group of panel will attach with a one converter. Similarly, the other group will attach with the other converters, and like that multiple converters will connect with different groups, and then all will connect with a single DC tie line, and then and go to the grid with another DC to AC converters. Both have own merit and demerit, right? So for example, if I will think about here in a string inverter side, here the main merit is you have one converter. So I will say the loss, first of all, the loss. So one converter means we have a few switches with respect to this one. Here the number of switches is less. So you can say the losses is less here. If another thing is that the control side means if you have the one converter, so you are going to control one, right? So all the control protection circuit, auxiliary power supply system, and everything will require less here, right? In this system. But the demerit is this is less reliable. Means that in a in case suppose any failure will occur on one switch, then what will happen? You will see that entire system will shut down. right? This is the thing. Another issue with this string inverter is this converter is suitable for large power. For example, these panels are for the megawatt range. Is it okay? We can connect with this megawatt range of power with one single inverter? Answer is no. This is not possible, right? So here, these are the challenges is here because this 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 issue is because of the limitation of power electronics converters. One single converter cannot handle with the 1 megawatt range of power or more than a megawatt, more than 1 megawatt range of power. Generally you will see the 40 kilowatt and 50 kilowatt power for the converters, right? So these are the limitations here. Similarly, in the microinverter side, good thing is that here this is more reliable, means if any fault will occur on one switch or one converter, so the one small group of panel will not work but rest will work. So this is more reliable. If you will think about the uh, size of the plant, here we can go with the multiple, or we can say the 10 100 according to your choice. You can go with a big to big number of solar panels. You have no issue because just you are connecting in parallel, so you will make a group and just connect with one converter and attach like that. So these are the flexibility you will see here. With the time you can add on your panels and you can make a large bigger system like that. But yes, the demerit side, if you will come, then you will see here the losses is little bit more with respect to this, and as well as here the required auxiliary power supply and converter protection circuits and all those controls are will required here. So this is a little bit costly, you can say in one word. But algorithm complexity side, both are more or less same because the same converter control will apply here for one converter or maybe for the multiple converters. The control complexity wise same, no issue. But yes, but supporting devices will be the costly one here. But the question again, where, in which conditions we will choose which one? If you are going for a small system, the direct answer is string inverter side. You can go for that. For example, rooftop solar panel. So simple, directly you can go with the string inverter side. And if you will go for the large panel, just like a PV park and all, then that time you can choose like a micro inverters and all type of solutions. But again, here in this today's lecture, I will discuss about the control side. So the same control will applicable for the both. Whatever system you are going to choose, you can apply for both, and that will work for both conditions. Next is the control objectives. So what are the objectives we will handle here through our control? So the mainly you will see the whenever we are going to operate a solar panel with the grid, the first objective is maximum power extraction from the panel. Right, this is the my first objective because the solar panels are not like a fixed power source, right? If you will look on the characteristics of the solar panel, then you will realize that solar is a variable power source. Means according to the your operating voltage, it will supply the different powers, right? And why this is like that? Because the solar system have variable input impedance, right? We can say like that. So here, so the maximum power extraction is the key part when we are going for the solar panel. So this is the first objective. Another objective, you will see that, as I told, so we are going to consider few local loads, right? So when we are going for the local load, so definitely the load demands and the fulfill those load demand is also another key issue. And then after that, we are going to integrate with the grid. It means that solar power is DC, so DC to AC conversion, as well as during the conversion, fulfill the grid codes are also important. Fulfill the grid code means we will we will see the what are the grid norms are here. So first of all, you can say the first grid norms is, you can say, the frequency should be according to the grid frequency, so that our system will synchronize accordingly, as well as the voltage should be also according to the grid code or grid norms, you can say that, or in worst condition you can say we should in the limit of that. So this is, if we are thinking for the three phase, then definitely the phase matching is also another grid code. So these are the key parts of the for the integration for according to the grid code connection side. But after that, if you look on the power quality side, then another norms is that power quality issues. What is the level of power? What is the amount of power? And accordingly, we should follow the grid quality, or we can say the power quality, or you can say the current quality. Just like you can say TSD, total harmonic distortions, means the total harmonic distortion should be less than the 5%. This is also the power quality side, one norms for the grid integration. So we should follow all those things, right? So we will go for all those things, and then and these all the objective who will fulfill? Our control will fulfill. And these are the basics things, basics norm when we are going to integrate with the system. Okay. But the another question is here, when we are thinking for solar panel and the integration with the grid and then all those local loads, then you will realize that this system will work for how much hour? Then you will see that it will work only for the 8 to 9 hour only. Mainly in Indian conditions, you can say that your system will start working from morning 8 a.m. until evening 5 p.m. on an average, I will say. So in this situation, then you will realize that the system is working only for 8 to 9 hours, right? And this is not a cheaper one. This is a very costly system, right? So if this is working for only 8 to 9 hours, it means rest 15 to 16 hours. What is the use of this system? The system means all these panels, all those converters, this is the capacitors. You will see this network, then you will realize this is the grid connected network, actual network, and you will see here this system, this portion will not work in the night. Means this panel, these capacitors, this DC converters, another DC link capacitor, this voltage source converters, all those control algorithms, filter, and then this is your interfacing inductor. So these all will not work in the night. In the night time, this all is not going to work, and this is extremely costly things, right? And so for what hour, for how much hour it is not going to work, then you will realize this is evening 5 to morning 7 or 8. So you can say this is 15 to 16 hour, this will work, and rest hour this will not in use. It means the if I will think about the utilization factor, what is the utilization factor of the system, then you will realize the utilization factor of this costly system is one third because of the timing. Means 8 hour it will work and the rest hour it will not work. And this one third only when we will utilize all those equipments on full strength. But this is the ideal condition, only this will possible, otherwise it will not possible. Means that the solar radiance will change, means sometimes solar radiance will low, sometimes it will be on the peak level. It means the utilization of these components is also not all 8 hours with the full strength. Definitely, when the solar radiance is less, then the stress will also less, utilization will also less. So, on an average, you will see the utilization of this entire system is not one third, it is one fourth around, or you can say this is around 25%. You will see the utilization of this component, entire system. Then question is again here, so is any process or is any way so that we can use this some portion of this system in the night time also? But yes, definitely in the night time, solar is not available, so we will not generate power. But yes, for different purpose or different way, we can use this system or not. The answer is yes, we can use it. Means this portion at least, means this DCC capacitor, this VSC voltage source converter, and this interfacing inductor and ripples and the ripple filters, we can use in the night for different purpose. Means we can use it for the reactive power generation, we can use it for the nonlinear power generation, or we can through this way we can support the grid in the night time through this operation. Definitely this is not going to work because in the night solar will not available, so we can use it for those purpose. Means through this way we can generate the reactive power. And the similar like a statcom. What is a statcom? If you look on the circuit diagram of the statcom, so that statcom is nothing. Just you will see the one converter will attach with the tie your grid connected wires in parallel, and then attach with the one capacitor. And this will the purpose of this is generate the reactive power and fed into the grid. Means we can use it as a statcom. Also, we can use it as a d-statcom also. Here we have a local loads, so we can fulfill the nonlinear load demand of this load, because this load may be linear or may be nonlinear. If this load is nonlinear, so on that situation, this here the nonlinear current will require, right? So in the night time, you will see this load is taking power from the grid. It means what? This in the night time, this load is taking active power, reactive power, and all those nonlinear power. All different types of requirement of this load will come from the grid, right? But if we are able to operate this system in the night, so that we can generate the reactive power and nonlinear power for this load, at least for this load. So what will happen? These two type of power will come from this side, and the one reactive power will come from the grid. So through this way, we can create a grid supportive behavior, right? So this way we can use it in the night time, right? Another issue is the nowadays you know that the we are moving for we are moving towards the electric vehicle sides, right? So the where we will attach this electric vehicles, then definitely you will see we will attach with the grid on that junction, or this junction is also known as PCC. You can see the point of common coupling. On that junction, we will attach our vehicles. So vehicles will attach with those junction through one adapter, right? So adapter means what? If you will think about a or standard adapters, then that is good. Means you will take the power from the grid and convert into DC, and then you will charge your battery of the electric vehicles. This is the standard behaviors. If someone is going to use those standard charger, then this is good. But in other way, in Indian markets, I will say everyone is not going to use those high power adapters. Definitely you will someone will go, majority of person I will say, will go with the additional charger, and those chargers will be based on diode rectifiers. And still in India you will see the so many cheaper chargers are available in the markets, which are based on these four capacitors and the one capacitor, four diodes and one capacitor. Diode bridge rectifier, so that you will take the power from the grid AC power and convert into DC, and then definitely this is pulsating power. So pulsating current you will see here. So just attach one capacitor, so that here you will see the current is more or less approx to the DC, and you can charge your battery and everything is okay for you. Sometime if you want to regulate this, so sometime you will see here one step down transformers, cheaper small step down transformers, and then you can use these things. If you will look on the output side here, nothing, no issue, everything is fine, right? And but at the same time, if you will look on this input side, what is going to happen? Here on the output terminal means we are going to attach our charger and take the power and charge our mobile or charge our electric vehicle. Then this side, if you will look, then you will realize here the currents are absolutely fine for your device, for your battery and all, and everything is okay. But here on the input terminal, what type of waveforms you are going to find? So you will see here in this output input terminal, the currents are like this. This is the current waveform of that. If this is the current waveform on the input terminal, it means what? It means through this charger, we are going to pollute this grid. And in the current conditions, it is happening. But since we are using those cheaper chargers only for the mobile side, so the current is in the milliampere. So that time this is not an issue. If the current is in the milliampere or 1 ampere and 2 ampere, then this is not a big issue. But just to think, if you are going to use similar type of cheaper chargers for the electric vehicles, where the current is maybe sometime 100 amperes or maybe 200, 150 and like that, so what will happen? Then that time ripples this ripples will pollute our grid, right? And this is a very serious thing for the grid side. If grid harmonics are we are intentionally we are going to inject in the grid, we can say on one way, and this harmonics will directly impact on our transformers, right? Transformer heating, line line side. Another you will see the increment of the corona effect, right? And also some other electronics equipments also, because of the resonance. Means this harmonics will impact on all those components which are connected with the grid, right? So this is the key issue, and now this is also one bigger challenge here. So if someone is going to use the cheaper charger, and we can't deny these things, so someone will not use these things, because everyone will favor some cheaper equipments. And on output terminals is okay. Only the problem with the input side, and no one is going to think about that, right? So as a operator PV, or as a plant, we can take care of those things, and we can support the grid to handle those type of nonlinearity. So that is the way, that is the target. Means that majority of you will see the majority of commercial chargers, commercial vehicles will attach with the grid in the night time mostly. So if those are going to connect in the night, the same time in the night time, our solar power plant is also ready to handle those harmonics, or we can say generate our harmonic requirement, local harmonic requirement. So this way we can use this circuit. Main purpose is in the night side, night time when solar will not there, and then this vehicle will connect. So what we will do, we will sense the nonlinearity requirement of this converter, this connectors or these chargers, and we will intentionally generate that harmonics here, and intentionally we will generate those harmonic current and fit to that, so that the only active power will come from the grid, and rest all those nonlinear current will come from the converter side. So through this way we can handle those things. But the question is how this will happen, and who will take care of those things, and how these things will mitigate, right? So for that purpose, we will use the control approach. So the basic control approach is like this. You can see here on this screen, the first time here, from the input side, the PV is coming, right? So PV power is coming from this way. So this is one way supply. This power is coming from this way, and this power is coming on the converter, or we can say on the PCC, means the converter, DC to AC converter, and then this is coming on the PCC. And then on the PCC, you will see you have one load, right? So the local loads you can say, and then also in between the power supply system here, the PV power is coming on the PCC. You will see in between we have one big capacitor banks on the DC link. So definitely once when we are going to attach one big DC link capacitor, so definitely some power will lose there for maintain the DC voltage. So those loss will consider as a load here, and we can say that is power loss on the DC link. So that's why the arrow is outwards. Similarly here the arrow is outwards because the power is going and this power is coming. These are the unidirection. But after that, this way we will calculate the after this fulfilling the load demands, is we have enough power or this power is less for that. If the power you will see the some extra power we have, then those power will go in the grid, or if this power is not sufficient for this to load, then that time power will come from the grid. So that's why the arrow is bidirectional in nature, and then this shows that the grid is going to behave here as a sink and source, and this is on the PCC, right? This is on the PCC. PCC means on the junction, right? This is our PCC, means where this solar portion is connected, and this is the grid, this is the grid, and these are the loads. So all the three things is here, so that's why the name is PCC, point of common coupling. And some papers and somewhere you will see CCC also, right? Common connecting point also, like that. Okay, so these are the powers. So the beauty of this point is here on this point we have one grid point, the grid connected, and then we all know that the grid voltage is constant. Whatever power we are going to fade or take from the grid, in both conditions you will see that the more or less grid voltage is constant. Whatever power oscillations, power increment, power decrement, power flow, everything will monitor or regulate through the current, right? If we are going to fade the current, then that time you will see our current and voltage is out of phase. If you want to increase our power, then you will see the current magnitude will increase. If you will take the power from the grid, so that time you will see current and voltage are in phase, and the amount of power will depend on the current. So more or less on the PCC the voltage is fixed. So what we can do, if voltage is fixed on this terminal, so we can divide this power to the voltage magnitude mainly I'm talking, because this is AC voltage. So if you will divide this term to the voltage magnitude, so what you will get? You will get PV component, right? We can say equivalent current component of PV, equivalent equivalent current component of PV. So we can say this is IDPV. Similarly, if I will divide this power to the voltage magnitude, so we can say that is what? Grid, grid power divided by grid voltage magnitude. It means grid current magnitude. Similarly, if I will divide the load power to the grid voltage, so we can say that will be the load current magnitude. Similarly, DC power loss will also called as DC loss current component, like that. So means finally all those power we can derive in the terms of current, right? And finally, what will happen? The final term will come through this way. So this is the input one IDPV minus beta DC. This is the loss because of the DC link capacitors, some small losses because of the loss to maintain those DC voltage. So minus beta DC, and this is minus load. So this two will subtract from that, and then finally it will come a grid current current reference we can say, or grid current magnitude we can say that, right? And this is positive or negative, it will depend, it will decide the grid is going to behave as a sink and source. What if this is positive? It means that some power, some amount of power is going inside the grid. And if this term is negative, it means some power is going to come from the grid, right? So this, like this way we will see that. Okay, so the here in this entire system, the bigger problem is this one, load side. Means that, as I told, so whatever power we are going to generate and power we are going to feed in the grid, here this power is not only, I will say that this is not only active power, right? As I told, so this power, what amount of power is going to come from the PV, we will not going to feed directly in the grid, right? Definitely we have some loads, and our objective is, first of all, we will try to fulfill the load demands, right? Here, local load demands. But the load is not linear. So here, load maybe sometime it will demand some nonlinear powers. Some 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 nonlinear power demand will come from the load. So on that situations, we will convert this current not exactly in a according to the grid current reference. Here we will convert in the two part, some amount of nonlinear current as well as some amount of harmonics, sorry, some amount of active current component we will derive. Means that here, first of all, we will sense here what amount of nonlinear power requirement is on the load side, and then we will, during our conversions, we will convert and try to match those load demands, right? So this is a very critical thing here. So how you will estimate that demands here? Here, if you will not able to estimate, then what will happen? The first issue, first question. If we are not able to estimate the load nonlinear current demand of this load, then what will happen? Then you will realize if we are unable to uh, estimate the demand, nonlinearity demand of this load, so that time you will see this converter will not generate according to the load. So two type of cases you will see. The case one, once when your estimation is less than the actual one, means whatever you have estimated, that is less than with respect to your actual demand. So what will happen? So if you will, your estimation is less, so your this converter will generate nonlinear power less because of your less estimations, so less power will come here. So on that situation, you will see this load will take less amount of nonlinearity from this side, and rest all will nonlinearity will come from grid side. Means load will take according to the load demand, but here we have the two connections, one is the grid and one is the converter, right? So if your estimation is less, so the some amount of portion is come from this way, and rest will come from grid to fulfill the load demand. So in this situation, your grid current will face some harmonics because of the less estimation. If your estimation is higher than the load demand, then what will happen? If your estimation is high, so you will generate much more power, more nonlinear power. If you will generate more nonlinear power, so the according to the load demand, the load will take that one, but rest will go inside the grid. Means you are going to feed those nonlinear current inside the grid. Means if your estimation is less or more, in both conditions your grid will face. So here the accurate estimation of this nonlinearity is very crucial point here. If you are capable to estimate, then only you can say you are not going to create stress on the grid, right? So this is the one challenge here, challenging thing. So for that purpose, in this system, if you will go for the literatures, then you will see hundreds of control techniques are available in our market, in our society, right? And everywhere you will see some issues is there, right? For example, the most popular one is DQ control, and then here you will see in the DQ control, this control is also known as commercial controls. Means the most of the industry is mainly uses these things, but here the issue is on the dynamic side. Means that here D and Q components are DC components, right? And your grid is weaker, so that time you will see in this D and Q components some second harmonics generates. So to mitigate those or sort out those second harmonic issues of these components, you will see low pass filter generally uses on that. When you are going to use the low pass filter on this component, it means you are going, and definitely the low pass filter will be the first order or second order. So definitely according to the order, you are going to create some delay. And according to the delay, delay means what? Your estimation errors. Delay means your estimation errors. So here, because of this, you will face some delay, and then that delay will generate some uh, error on that, right? Because of the estimation error, right? Similarly, you will see the SOGI. This is also most popular one, but the issue with the SOGI is n- not capable to eliminate the DC components, right? Similarly, you will see the other one is LMS, LMF family, right? This here, again, the issue with the weight initialization and other things. Similarly, the Kalman filters, right? So, so many things you will see in the literatures, and everywhere, sometime some will face on the dynamic side because of the delay, as someone will face on the complexity level, means your requirement of processor memory size, or I will say the cache memory is high because of the lengthy calculations, just like a Kalman and all. So these are the few issues you will see on the few different techniques, right? So to mitigate all those issues, here we have tried to use this one, ANOVA kernel stochastic gradient descent algorithms. So this ANOVA kernel stochastic gradient descent algorithm, this is based on the neural networks, and but again, this neural network is not, I will say, the not traditional neural network, so that you will use the data and then train that, and then that will work. No, it is not like that. Here training is not required any pre data, so that you will train your algorithms, or sort out your find all those constraints, and then your algorithm will run accordingly. No, it is not like that. So this is single layer neuron structures mainly, I will say. And then this portion, stochastic gradient descent algorithm. So this is your single layer neuron. And here I have used the ANOVA kernel trick. This ANOVA kernel trick is mainly for the mapping. Mapping means here, here this filter will as work as adaptive. Adaptive means here, through the error, according to the error, we will map and we will predict the error. We are not going to only predict the next stage requirement, as well as we will predict the errors. And if we are capable to predict the error for the next step, then our updation will retune. Retune means we will retune according to the predicted error also. So for that purpose, here the kernel, ANOVA kernel has used here, right? So this ANOVA kernel is for the high dimensional mapping. Dimensional mapping means we will generate the relationship, linear relationship between the all those errors, and then predict the errors accordingly, and then that will use in the next level. So here, this entire operation you will based on like this, and this will look like a you can say the adaptive one, means the data is coming, means the current is going to come, means this is our load current, and then this load current is filter out. So here this filtering definitely based on our techniques, but after the filter out, whatever component we will get, we will compare with our actual one. So whatever we will predict and what is actual one. So through this way we can say this component. So for example, here in this system, how we will predict these things, means this information will come from the grid side, means what amount of power current, nonlinear current we have generated, and what amount of nonlinearity current come from the grid or gone inside the grid. So that one. So through this way we can estimate what is the error here. Through this way we can see the error, and accordingly we will update our weights, right? But here in this updation, this is not according to this one. Here in this updation control, we will use those mapping, and then that will generate the the according to the error, as well as the error for the next step, means according to the trend. So how we are going to converge. So accordingly, it will work like that. So also you can see for the three-phase system, it look like this one, and this is single layer neurons. So here no training, nothing not required. Here definitely one or two pa algorithm parameters you can see, but yes, this parameters is not based on the heat and trial. This algorithm parameters will generate according to our stability analysis. I will also show how we can generate that, and how we can calculate those uh, algorithm parameters, right? And that will use here. So that's why this is single layer neuron, but this is suitable for all type of every type of system, every type of rating of the systems. It will not depend on the rating of the system, means you are going to use for which type of plant. They say plant is a smaller one or bigger one, whatever plant you have, it is suitable for all, right? So it is not dependent on those things. Okay, so these are the structure of the neurons, single layer neurons. Okay, so the key part of this control is here in this key equations of this AKSD control algorithm. So you will see that here the three things will require. One is the load current, one is the unit template, and this is your errors, we can say, or you can say the weight updated errors, we can say like that. So through this way, what is this? First of all, this one U, I will discuss that. What is U? U is a unit template, means that, as I told in initial slides, so grid synchronization is also very important here, and most of the times you will see the grid synchronization is based on the PLL. Generally people uses PLL for those things, phase lock loop, but when you will go for the MATLAB, and then you will directly you can use the PLL. But I will suggest once open the inside this PLL network, or your diagram of the PLL, actual PLL diagram. When you will focus on those things, what type of diagram, what type of network or connection have you used inside the PLL, then you will find that inside the PLL you have used one derivative term, as well as you have used PI controllers inside the PLL, but mostly students directly take PLL from the MATLAB library and can use. But when you will look inside that, then you will realize there is one derivative, as well as one PI controller inside the PLL. So the issue is this thing is that, so PLL is tuned for a particular error. Once your error is changing or your error is deviating, so the PI will need to retune, right? If you will not tune, then definitely it will work, but it will take longer time to converge or settle down on a steady state value, right? So this type of things you will see. But here in this situation, we will not use PLL. So on the place of PLL, we can use this unit template concept. So I will discuss that what is this unit template concept, and what is this unit template. I will discuss those things. So this is that term, this is for the phase A. So this is phase A load current, this is unit template of the phase A, and then this is calculated, sorry, weight updated form. So for this way you can see this is the prediction error. So this is the load current, and this is our predicted one. So you will see this is your predicted error will come from this way. Similarly, this error, as I told, we will map this error. So through this mapping, you will see in this mapping we will generate one weight, or we can say not generate, calculate, I will say this, we will calculate this weight. But this updations here is ANOVA kernel trick, and this ANOVA kernel trick is based on these errors, so that this in this high dimensional mapping we will also predict the error for the next step. And in this calculations we will use the autocorrelations between the all those errors and adaptive design parameters for the next step. So if we will use those, and then we will calculate the updated weight, and then that will use for the final updation. So this is the key structure here, and this is the I will say the mapping space for the ANOVA kernel. So the meaning of this is that the errors are going to decrease exponentially. So this is exponentially decrement of the that is showing here, means see how exponentially it is decreasing. And no matter where is this is going in this direction, in negative direction or positive direction or any other axis direction, whatever direction the error is moving, but finally it will converge on the close to zero exponentially. These things are shown here in this picture. Okay, so so here this is for the phase A, but for phase B, the same set of equations will use. Only you will see here suffix B has used here, means the phase B current, phase B unit template, and phase B error, and like that. Similarly for the phase C, same set of equations will use for those things, those one. So we have two options. Once we can go for the code and just like a type like a write one code one by one and calculate and generate that. This is the one way. Other way, if someone is not comfortable with the code, then we can go with the block diagram also. This is the block diagram of the same code, what the code I discussed shown here. This all the calculations we can do through this coding. Means internally nothing else here, just the taking the square, multiplying with the factors, and then adding and all. So you will see that. So this is the block diagram of that control here. But again, the question is again here. So here is the two algorithm parameters you can see here. So how we will find out the value of these two parameter, or how we will decide that? Is this is this number will depend on the system? Answer is no. It will not depend on the system. It will depend on the stability criteria. So in these situations, what we are going to do, we are going to use the stability criteria. So what we will do, first of all, we will formulate the state space matrix. So what we had done, this is the actual current error equation, sorry. In this error equations, we will re-put all those values of this data. So for example, this is zeta PA. So what is this? So this one is zeta PA. So we will calculate that, and then we will put here. And then you will see that if you will do that, definitely this is a bigger one. So few portions I have taken as a constant. For example, this calculation I have shown like this one, phi dash, and then you will see the new dash like that. So reframe this equation, we can write like this way, right? So this is that, and then again, if you will, here is zeta PA, right? So zeta PA, on that place of zeta PA, we can take this one here, and then we can place here, and again you will see this is the final equations. And in this final equation, this term is what? This term is A, right? So this A, we can say this is A is phi dash I into nu dash UA and UA transpose N. So this is A dash, or we can say this is a state transition matrix, we can say like that. So if this is the state transition, if this is the state transition matrix, so what we can do, then we can go for the eigenvalues calculation. So here we will just multiply with the unit template and then reformulate all those equations, and then after that we will apply the eigenvalues approximations. So here, what is that? Here we have assumed that this matrix is a discrete time factor of n, and then have the matrix eigenvalues is like that, and then we will apply the eigenvalue theorems. According to the eigenvalue theorems, you will see that if this diagonal elements mainly, the non-stationary system with the magnitude is less than 1, then the system is asymptotically stable, right? So this is the basic theorem of that. All those eigenvalues of the symmetric state transition matrix, right? So what we will do, we will first of all try to find that eigenvalue, and then we will intentionally put less than 1. So if you will do that, then you will see that here is our constants, right? And no, these are the not constants. These are the two factors which we have assumed here, phi dash and nu dash. And now we will put again here in this equation, the last equation, phi dash and nu dash. If you will put those things here and then reformat that, then finally you will find this is the relationship. In this relationship, omega is the learning factor. So through this way, finally you will see this is the relationship. In this relationship, this portion should be greater than this one. So what should be the suitable value for omega so that it will bigger than that? Definitely this is omega is non-linearly related with this one, because omega is here as well as omega square you will see here. So if we have this choice, so through this way we can choose one value of omega so that it will bigger than that. And this is not a big issue, right? Through selection of omega in such a way that it should be bigger than that is not a key issue. So we can choose that, and then that will be we will use there for learning rate or for tuning. So this is the key portions or key parameter tuning of this algorithm, and through that way we can use that. And after that, what are the performance? This filter, this is actually filter, right? So this filter is for the fundamental component instructions, right? So here the capability of this filter has to tested on this signal. Suppose this is the signal, and the signal have 37.34% TSD, right? So in this nonlinear current, I have applied this one, ANOVA kernel trick, and then I would got these results. So through this way, you can see that how perfectly it has uh, it has extracted the fundamental component of that. So if this is the fundamental component, then what is rest? This is rest total is nonlinear current. Means if you have this one, so just subtract to the actual signal and then rest is your nonlinear currents. So that's why here we have used this concept, right? Similarly, that this is for the simulation, but the similar concept has used for the experimentation also. So suppose this is our signal. So how this filter? I'm not talking about the solar and all. This is only for the filter, whatever filter I've discussed here. So the same filter I tested for this signal. So through this, from this signal, I have extracted that active component. This is that. Similarly, for this signal and this is that. Means that the nonlinearity of this signal may be anything, but this filter will extract the fundamental component very accurately. Definitely, in this entire calculations, we have one step delay. You will see that, then you will realize here we have one step delay because in the series, suppose this is in the parallel, but here in the here, yeah, this one, this is one step delay you will find, but this delay impact is less. Delay impact is less here in this system because as I told, here we are not going to calculate the error and use to update. No, here we are also predicting the error for the next step. So through this way we can sort out those delay issue, right? So through this is the key concept, or we can say that's why the name is ANOVA trick, right? That has used here. That's why you can see here the performance is very accurate here in some way, right? And also this is a compare with the different techniques. So you will see that with respect to all other techniques, so this is very pure, you can say that, less oscillatory and the very smooth in every time. You can see that on the on the any dynamic condition or maybe during the steady state conditions, every time you will see the performance superior with respect to all others. Finally, we can use this for our system. So suppose this is our system, right? So here we will use that. This is our control structure. This is solar panel and then directly attached with the DC link, and this is our DC link capacitor, and this is inverters, and then you will see this here the filter, sorry, interfacing inductors, filter, load, and then this is the grid. So in this system, the same control has used here, right? So this is single stage. So again, we will try to fulfill all those objectives. Here the key objectives are maximum power extraction, power conversion DC to AC, to follow the grid code for the synchronization, like a frequency, voltage matching, phase matching, right? Also the TSD match, TSD under the limit. Also they improve the power quality of the power supply, TSD under the limit. Also the D-statcom action when the solar radiance is zero, right? In the night time, we can say this is D-statcom action. Also the power management means generated power is used to satisfy the load demand. After fulfilling the load demand, rest power supply go to the grid. So these all six objectives will fulfill through this control. So finally, in this control, as I told, PLL we will not use. So which component will decide the frequency and how the frequency will match here? So for that purpose, here the unit template concept has used. Unit template concept means frequency means definitely frequency is this if grid has some certain frequency, so all the grid components will also follow those, right? So for example, if grid have 50 hertz, it means what? Your grid voltage also based on that 50 hertz, grid current is also based on the 50 hertz, right? If grid frequency is 50.005, what it means? It means that grid voltage is also based on that, and then that is 50.005. So what the trick is, so we will take all those grid voltages, and after these are the voltage phase A, phase B, phase C, and after that we will divide this voltage to the voltage magnitude. What is the peak magnitude of this voltage? We will calculate, and then we will divide to that. How we will calculate? Just go through this way. Root under 2 by 3 VA square plus VB square plus VCA square. Through this way, you can calculate the peak amplitude of the grid voltage. And through this way, you divide all those signals to this magnitude. So what will happen? This signal, this is a sinusoidal signal. This pure sinusoidal signal will becomes unit template. Unit template means the magnitude will become in between -1 to +1, because the peak, what is the peak? Suppose this grid voltage peak is 220. So you will calculate this Vx, and then Vx will be 220. So if you will divide to the 220, so you will see that the magnitude peak is 1 because of the division of 220, and in the negative half cycle you will see this is minus 220. So that time you will see the minus 1. It means this is the signal in between minus 1 to plus 1. That's why the name is given unique template. And these signals will use for the synchronization. These signals will be used for synchronization, because whatever grid frequency, we will not calculate the frequency, just we will generate the signal based on that frequency. If frequency is 50.005 or 49.999, so this signal will also based on that, right? Because this signal is coming from the grid. So accordingly, these signals will according to that. So this is the for the grid synchronization purpose we will use here. Another component, as I told, is the dynamic reflection, means the PV side, right? So how we will calculate that? So the PV side, the PV power, just as I told, so how we will calculate when you will divide the PV power to the voltage, and then you will see the AC current equivalent of the PV, right? So this is that. So how we will do that? So just we will take the PV power and divide to the 3 by 2 Vx. So through this way, we can say that this is AC component of the PV DC, right? So that way. And this is also in some literature you will say this is the feed forward term, right? And sometimes you will see this is a dynamic reflection component and all. But this is actually this is AC component of the DC PV power, right? So this is that. Another, you will see the DC link loss component. So how we will calculate that? Simple is that we will go for the errors. What is the DC link voltage, and what is the DC link reference? So we will see the difference errors. So this is the actual DC link voltage. This is the DC link reference. Similarly, this is DC link reference. This is actual voltage. So you will see this is error. So if this is the error, so what is this? This is a PI controller. So this is GPI. This is the proportional controller, and this is GI integration G0 to 2, 0 to T DN. This is your integral controller. So finally, this is PI controller, means we are calculating the error and feeding the PI controller, and then PI is going to give this component, and this component is known as DC link current component. And this is the grid DC link current component to maintain the DC link voltage, right? This is, other word we can say this is the loss component. Sim Other is the load current. We have those filter, ANOVA kernel stochastic gradient descent filter. So what we will do, we will use this load current unit templates, what we have calculated, UA, UB, UC, and then zeta PV, this is a calculated term. So we will use these three here to calculate this these are the estimated load components. These are the three-phase estimated load component. Then finally, the net estimated active active load power component is addition of all these three and divided by 3. So we will take the average of that. This is our net estimated active power load component, right? So this is the average of all that. What is the meaning of this? This component will go in the block diagram what I shown, right? So you will give into that, and then this is the output of that directly. And after that, once you have all those components, so you can calculate this one. This is what this is a grid current. But if you will focus on the initial side, that time I told, so this is the PV power representative, or you can say the PV power current, right? So PV power current minus minus DC link loss minus load is equal to the grid. Initially I told, but here you will see this is not like that. It means here these are the loads minus generation. Load, these are both are the load, right? So this is the DC link for the DC link loss, and this is for the load. So the summation of that minus generation. So what will happen here, when the generation is high with respect to the load, so you will see some negative term. When your generation is less with respect to the load, then you will see the positive term, right? Why like this? This is according to the grid behavior. Whenever we will take current from the grid, we will take power from the grid. So that time you will see the grid current is in phase with the voltage when you will take the power from the grid, right? When grid is behave like a source, so that time grid voltage and grid currents are in phase, right? So in this situation, this term should be positive when we are taking. But when we are going to feeding the power inside the grid, when you will feed the power inside the grid, so that time you will see this grid current is out of phase with respect to the voltage. Out of phase means 180-degree phase shift you will see there. 180-degree phase shift means just multiply with -1. So negative. So that's why I have taken like that. So this is out of phase. And why I'm comparing with the voltage? Because we here this is the my synchronization term, unit template. Means by using this unit template which is based on the voltage, means by using the voltage reference I'm going to trigger the synchronization term, right? So that's why again and again I'm comparing with the voltage. In the terms of voltage, I'm looking on that. What is the reference and the reference behaviors? Means that whenever I want to fade inside the grid, so that time this reference magnitude should be minus negative, or we can say out of phase. Once whenever I'm going to take power from the grid, so that time it should be positive, so that it did behave like a source, right? So that's why this is like that. And after that, this is what, this is magnitude, just a magnitude number, right? So we will multiply with the unit templates UA, UB, UC. So these numbers are according to the grid frequency and grid phase. So no issue with the phase, no issue with the frequency, because these signals are totally based on the phase behavior and the frequency. So just multiply with that, and then we will generate one sinusoidal signal with this magnitude, and then we will give the name of IGA. So this is grid current reference for phase A. This is reference for phase B and phase C for the grid current. And like that, we will use that. And after that, we will use the hysteresis controller. Means what? We will compare with these are the references. We will compare with the actual one, and we will generate the error. Means that this is the references. These are the reference terms, and these reference will compare with the actual current, and then see the errors and get to the hysteresis controller. And through this hysteresis controller, we can generate the error. Sorry, switching. So according to that, our converters will fire accordingly. So through this way, we can control that. But yes, this is for the grid connected solar PV system side. But just assume in the night when grid is not night time when our PV is not going to work. So that time what will happen? It means that time this is zero. That time this is zero. If this is zero, so what will happen? So this is the only term 5p, and then this 5p will be used here. But that time this 5p will be the positive. So it means the power will come from the grid, right? So that time this term will positive, so power will come from the grid. You will see that. So in the night time or daytime, system will automatically react. It will not required to manually change the controllers or anything. System will automatically change the nature behavior according to that, right? So this is the control final control behavior of that. This portion is for the PV MPPT, the upper part. This is for the PV MPPT, and then this one is the voltage unit template generations, and then this is the estimation of unit template, right? And then that will be used for the load components. These are the load components, and then all will calculate here. This is the final one, and then you will see these are the IGA reference, IGB reference, IGC reference, and then all references going to compare with the actual one, and then going to the meet going to the hysteresis control to generate the pulse like that. So this is the basic control structure for that. Okay, this is the simulation model of that. That is not important. This is the hardware controller system where this all the things have tested, right? In this system you will see the system I have used. This is you can say this is DSpace, right? For the all those controllers. This is solar simulator for that. PV characteristic generations. This is our DC-DC controller and DC-AC controllers, both converters, sorry, both is here. These are the current sensors, and then grid connected mode. The actual grid I have used here. So this is grid connected mode. So all the interfacing inductors and all these things will be seen here, right? So this is the terms here. Finally, in this testing, you will see the first of all tested on the under unbalanced linear load conditions on the simulation. Definitely, this all the testing is on the hardware as well as simulation, both side. You will see that. So this is our linear unbalanced load. Means this is the load conditions. So load current is pure sinusoidal, but on this point here you will see unbalanced. One phase load has gone. But then that time you will see how this is going to react. So these are the grid voltage, grid current, load current, VSC current, and then DC link, IPV, PV power, PV voltage, PV current. Like then you will see the load component, DC loss component, PV current component, and then AC grid power component, means references. Like this you will see. Here, this is gone, right? If one phase has gone, then you will see this one. Grid current reference is also decreased. Decreased means here, suppose this is around minus 16, here this is minus 18. Is this decreased or increased? So, as I told you, the negative grid current reference is increasing, right? Minus 16 become minus 17. It means what? Means your more power you are going to feed inside the grid. Means here this negative term is only for the current reference, means negative polarity, sorry, out of phase polarity you are going to generate. That's why this number is, but just look on the magnitude of that number. 16 becomes 17. It means one phase is gone. It means the load consumption is decreased. So the power feeding inside the grid has increased. So that's why this is gone down, right? So you will see that. And this is pure linear load. So that's why the TSD is also very less, around 0.48%. So this is the hardware one also. So you can see that this is the load unbalance point, and here after that system is reacting like that. So you will see the grid current is this one, but after that the grid current has increased. Grid current increased means the power feeding amount of power, what amount of power is going inside the grid is increased, like that. And then in these situations you will see the grid current TSD is smooth, this is 1.5, and then load is also linear, so that's why this is 1.9. So this is linear condition. Now we will see the nonlinear condition and unbalanced also. Unbalanced nonlinear conditions. So this is unbalanced nonlinear condition. So this is our load. So you can see here this is the load, and the load TSD is very high, and this is around 16.95%. So this is the load TSD, and this point one phase gone. So nonlinear unbalanced load conditions. So again you will see this current increased, magnitude increased, or we can say that decreased because of the negative terms. So means the more amount is going inside the grid. But the beauty of this thing, see here, this is highly nonlinear, but your grid current is pure sinusoidal, right? The impact of that is very less. Similarly, you will see on the hardware side also. So this is the load unbalanced side. So this unbalanced side, when it was unbalanced, load unbalanced, so but your grid current is pure sinusoidal. So it means your estimation is very accurate. So you can see here the load TSD is 27.3%, but the grid current TSD is around 2% only, right? It means so your estimation or your feeding is very accurate. Another thing you will see here, when the load is feeding, so that time this is VSC current. See this VSC current. This is not sinusoidal, pure sinusoidal, right? This is partial sinusoidal, you can say, right? And why this is like that? Because our converter is not only generating active power for the grid. Our converter is generating load current as well as rest all is pure sinusoidal for the load, for the grid. Means here this is the combination of both. That's why this is not pure sinusoidal, this is VSC. Means VSC is generating the linear current also according to the requirement. But yes, when the load was connected, so that time the requirement is like this, more requirement was, nonlinearity requirement was more. So that's why this is less sinusoidal. Sinusoidal behavior is less here, but here after the disconnection the requirement decreased. So you can see there, see that the VSC current is more sinusoidal because nonlinearity demand has decreased here, right? That's why. Similarly you will see here, if I will show the grid, sorry, VSC current TSD. VSC current TSD is 14%. This 14% TSD. Why? This is the combination of this one as well as this one. Because of this is like that. And as we know that the TSD, what is TSD? All all the harmonic component divided to the fundamental component and multiply with 100, then you will see that is your harmonic, right? Addition of all those magnitude of all those harmonic component plus divided to the fundamental component. So this is that. So that's why this TSD is less, because this is addition of not linear addition, right? This is not direct addition. This is based on the calculations. So that's why this is less, but this is, here you will see higher TSD. Okay, so similarly, other things you will see other type of behavior also during these things are tested under the grid voltage fluctuation conditions, means the over voltage conditions, and under voltage conditions also, means over voltage and under voltage conditions also the load is also disturbed accordingly, right? So you will see that when the voltage is over voltage, the voltage increase means what? Grid current will decrease. Voltage increases means grid current decreasing. That's why you will see this is decrement of the grid current. This is the negative terminology. So that's why this is like that. This is around 16. This is around 14, right? So 16 ampere become 14 ampere. That's why this is decreasing, right? Similarly, you will see here under voltage conditions. So here you will see the voltage is less, so current is increasing, right? Means both when voltage increasing or decreasing, but power is balanced here, right? So the amount of power, what amount of power is coming from the PV, that is constant. So that's why this current is increasing and decreasing because power is constant. Similar thing you will see on the hardware also. So this type of behaviors is here. So this is increasing and decreasing. So the terms is also like that. This is your over voltage conditions, right? So your grid current is decreased. So this is the decrement of that. Decrement because of the negativity, right? So similarly, this is under voltage conditions. This is increased because of the negativity. You will see that this is downside, right? And but the TSD is maintained in all. So here you will see 1.8, 2%, and the 2.7%, right? So this is the situation. But I will say here, in this situation, TSD is less, but here TSD is high with respect to this. Why this is like that? But here this is less, 1.8%. Why? Because TSD is ratio of all those harmonic component with respect to the fundamental component. Here the current is high. So here you will see the in this situation the current is 6.78 ampere here under voltage condition. So this is for this one. This is for this one under voltage condition. During the under voltage conditions, the TSD current amplitude is 6.78. But here over voltage condition for this one is this one. For over voltage condition, the current is around 5 ampere. So here the denominator is lesser, denominator is higher. That's why TSD is also fluctuating according to that. Similarly, also you can see the midway also here 5.8. So you will see that this is in between this one like that. Also, you can see the same thing also tested under the load and solar variations conditions. Solar variations means solar radiance has gone down and here the solar radiance has increased. The both the conditions when the radiance is low, it means the power generation is low. So grid current is also low here. So you can see that the grid current is low. But yes, load will not disturb total nonlinear load. Load is taking same amount of power according to the load demand, but only this one is changing, and this is changing. Then that's why VSC is also changing, and that's why the grid current reference component is also changing accordingly. Similarly, you will see here this has increased, so you will see the grid current reference is also increased like that here to here. If you will compare to this and then this, then you will see this is increasing, right? But the load is balanced here. Also on this screen, you can see that for different solar radiance, different types of characteristics. But yes, in each conditions, you will see the FPPT tracking is very smooth, and this is around 100%. This is according to that, and different power level you can see, and these are the behaviors for that. So how these components are increasing and decreasing. So this is upper one is the VPV, and this is IPV and PPV. So PV panels in the when the solar radiance changes and increases and decreases, then you will see the more or less voltage is constant. You will found not constant mean constant does not mean the exact one, but the change in voltage is lesser compared to the current and power. That's why here the change is less. But in the major significance changes you will see in the current, and then this is in the power, right? Similarly, you will see here when the solar radiance is increased, so the current is increasing and then power is increasing significantly, right? So this is the terms you will see that on different solar radiance conditions. The last one is then under day to night mode of operation. Under day to night mode of operation, it means that so in the daytime system is behaving like a solar power generation, right? So power is generating from the solar, right? So you can see the PPV. This one is PPV. So in the night time, daytime, sorry, power is generating. So when the power is generating, then power is going inside the grid. But in the night time when this portion is zero, so you can see this is zero, it means the PV power is zero. So that time load is balanced, load is nonlinear, but the grid current is sinusoidal. Load is load is nonlinear and PV power is zero, means power is not coming from the grid PV side, but the grid current is pure sinusoidal. Why this is like that? Because here our VSC, voltage source converter is acting as a showing the D-statecom behavior and generating the nonlinear current demand. So all those nonlinear current demand of this is coming from the VSC side, so that only active power will come from the grid, and then this grid current is pure sinusoidal, right? You can see this one, and this magnitude is less. Why? Because this magnitude is only according to the requirement of load current. Here the load current requirement is 2, so that's why this is like that. Similarly, that was the day to night. Similarly, here you will see the night to day mode also, means the night time, how the system is behaving. And then once the solar panel will come in the picture, so here PPV, once the panel will come in the picture, so that time you will see this will change the mode, and then again system will start working as a solar power generations, right? So this is the main thing. So here in the night time when the system is behaving like a D-statecom, so that time you will see this is the grid voltage, right? And this is your grid current. So grid current is pure sinusoidal, so the TSD is lesser. This is 1.8%. Load is nonlinear, so this is pure load. So load is 29% TSD. But VSC is only generating the only harmonic current. VSC generating only harmonics current, no fundamental. So what should be the TSD? So if fundamental is zero, right? Fundamental is zero. So we can say if fundamental component is zero, it means only harmonics. It means the TSD should be 100%, right? But definitely some amount of fundamental is there. That is very less. But the TSD is 95.42%. Means DSC is generating only harmonic current in the night time, and according to the load demand. So this is the D-statecom behavior. Also on the hardware, you can see that during the daytime how the system is behaving. System is behaving like a solar power generating system. Also, you can these things observe from these waveforms also. So this is grid current, and this is grid voltage. Whenever we will fade the power inside the grid, when we will fade the power inside the grid, so that time you will see your voltage and current will out of phase, right? Means that here in the daytime when the PV is generating power, so that time you will see both are out of phase. Both are out of phase. See here, this voltage and current, both are out of phase. Means power is going inside the grid. But in the night time, when PV power is zero, means PV is not generating power. So that time, this grid will supply power for the load. Power is not going inside the grid. Power is coming from the grid for our load. So that time you will see this current and this voltage both are in phase. Both are in phase, right? So through this way also you can observe power is going or coming. So through this phase differences in between, and this portion where the mode is changing. So during the mode change, this is not sudden change. It is taking some time. Why this is like that? This is because of the desealing capacitors, right? Because when you are thinking for grid connected mode PV, right? PV grid connected mode. It means you are playing with a big power. So big power means your PV capacitor has huge amount of power, right? But when you are going for the that time you will play with a smaller power. So that time this stored energy on the DC link will also discharge and then maintain the or support during the mode change. So this is that mode change situation. So here when power is going to become zero, so this is the mode change. So this is the mode change. Similarly, also you can see the power, PV power. So this is the same, both are the same situation. PV power, here is the PV power and PV power going to zero. And this is VSC. So in the daytime, generating load current as well as the grid current. So that's why like this. But in the night time, this is only generating the harmonic current. This is only harmonic current. This is harmonic wave currents for load. So that's why the load currents are constant throughout the day and night, right? No disturbance, no any compromise with this. Small oscillations you will see here on the BDC during the mode change, right? Small oscillations you will find because of this DC capacitor is discharging and going to change the phase and the current behaviors. That's why small dp you will see here. But again, it maintain that voltage and to maintain these things. But the question is again here in the night time when we don't have any source, and who will provide the power to generate this nonlinear current? The answer is grid. Means that in the night time, grid is giving active power to the load as well as active power to our converters, so that the converter will use those active power for generating the nonlinear currents. So here the current coming from the grid, when I will show this one, so you will see this currents. So in the night time, mainly in the night time, this current this current is 6.8, but the load is only 6.6, right? So this is 6.8, and here this is 6.6. Why this is higher? This is higher because the rest current is going to the converter. For what purpose? Uh, for generating the reactive powers and all. Okay, so this is the day to night mode. Similar operations you will say during the night to day mode, means the when the morning will come, then how the system is going to operate. Same type of things you will see in the night time. This nonlinear powers is nonlinear currents will generate through the DStatCom, and then load will take those things. And this is the grid current. This grid current is only according to the load, but here is the mode change when the PV power will start coming. So that time this is a mode change, and then you will see this during the daytime current is going inside the grid. Again, here you can realize that here both are out of phase, means the power is coming from the grid. Here both are in phase. In phase behavior means going inside the grid. So like this type of things you will see. And here this is totally seamless control. No manual things is that. Only once the power is not sufficient for active power generation, then automatically system is switching the behavior from active from PV plant to the DStatCom, and like that. And here we have the nonlinear loads. That's why we are going for the DStatCom. But if you are operating with a PV park and you don't have any local loads, so that time you can operate as a StatCom also. And then that time you will see this will generate only the reactive currents. Means your converter and capacitor will take power from the grid and convert into the reactive power. Reactive power means what? Current, when current which is 90 degree, 90 degree phase shift 90 degree with respect to your grid current, right? That's it. So this converter will do like that, and then you will see that the reactive power and fed into the grid according to the requirement. We can switch the behavior also, the statcom or statcom, according to that, and it will work for both things automatically. This is also your harmonic spectrum for the statcom mode. And this in the night time, the VSC behaviors, this is 94.7% TSD you will see on the VSC, because VSC is only generating nonlinear currents. These are the waveforms of the current waveforms for the from the converters, right? But this side load is taking 27.5% TSD, balance load day and night, and then grid current is a smooth but 3.1%. Since we have this statcom behavior, then only this is 3.1. Otherwise, what will happen if we will not go for this operation? Then this 27.5% you will see here, means grid will supply and load will collect, right? So that time you will see the entire stress of these harmonics on the grid. But since we have this operation, so this is giving extra support on that, right? Also, another thing is that uh, grid voltage unbalanced conditions means, suppose you are operating with a rooftop solar panel, and your system is connected with the distributed grids, or you can say domestic grid. So that time you will see grid is not uh, stiff enough, right? So that time your grid will be I will say the weaker, right? So the weaker grid means what? You will see the grid voltage unbalanced sometimes. So during the grid voltage unbalance, how your system will react? So this is the thing here. So this type of here you will see the grid voltage imbalance. So here you will see that this phase is 134 and then blue one is 101 and this is 91. So the total you will see these are the peak value, right? So you will see these are the totally unbalanced here, right? But this side grid current. So this grid current you will see this is 4.90, 4.3 point sorry 3.49, 3.49 and 3.49 means almost all the currents are constant and balanced. So this is the beauty of the control. So if any unbalance come from the grid side or any harmonics come from the grid side, that will not reflect here. That will not reflect here, right? So this is the beauty of this. So all the grid side disturbances also will mitigate and the system will react. Definitely, if this is the situation, then I'm not telling that so system is going to correct the grid behaviors. But yes, we are not going to correct this grid voltage behavior, right? But here what we can do, we are not going to contribute any extra burden on the grid. So this is the thing here, right? So that's why this is, you will see this is a balanced one, right?
सुना तो कर बात पूरी।
And then if
कहाँ
you
खड़े
look
रहे
on the if you look on the phase one,
भाई ये क्या था कि भाई ऐसे नहीं
if you
चल
will look
पाएगा,
on the phase,
सही नहीं आ रहा है, तुम लोग क्यों निकल लिए?
Please mute yourself.
if you will look on the phase side also, then you can see that these are the three voltages here. So the voltage side unbalance is around 26.11%. If these are the voltages 134, 101, and 90, and these are phasor diagrams of the all three phases. So you will see that this is unbalance is around 26.11%. But the current side you will see this is 0.86%, right? So this is the things, and through this way, this has controlled, and then control behaviors are like that. But this is in the three phase. One thing I want to highlight also. So here I have this control. What control I discussed? This is for the this system. This is for this system. Means this is, you can say, single stage system. Means no DC link. Sorry, no DC-DC converter here. We directly panel attached with this DC link, and then system going to work like that, right? But here, if if I will say uh, you are going with the two stage, so that time you will attach one another DC-DC converter here. So what is the merit and demerit of that? If you are going for the single stage, then definitely you can say you have merit that you have one converter, so the losses is less and easy to operate. But no, another issue with this single stage is that, so suppose you are going to play with this three phase. Three phase means here voltage is, suppose I will say 415 three phase voltage, right? So that time what amount of voltage required here on the DC link? So that time when you will calculate back, and then you will see this is around 700 volt. It means the panel voltage should be in such a way that the panel VOC is around 800 or 850 sometime. Then only you can connect with this BDC. But PV panel voltage 800 is a very big thing. A small panel, the mostly you will see the small panels comes with a 32 volt and 24 volt and like that. So here a lot of panels will require to connect in series and then match this voltage, right? So this type of scheme is okay when you have this large PV panels. Then only you can go with that. Then only your voltage will match with that, right? Because you are going to operate with the grid. So this voltage is fixed. So accordingly, your DC voltage should be, right? You can't go with any voltages here. So this is the key thing here. So normally these things not happens, right? So that's why you will see the most preferable for the small size panels are use one DC-DC converter here. So when you will attach one DC-DC converter, for example boost converter, so how you will operate? So no, that is not a big deal. Only a small changes you will see here in these situations. PV panel or PV current and PV voltage you are giving to the MPPT algorithm, and then MPPT algorithm generating the your DC voltage requirement. So what should be the DC voltage, right? So DC voltage reference you are calculating through this MPPT algorithms. Maybe you can choose any MPPT technique. So that MPPT technique will give the VREF. Here you will generate the VREF. But VREF for what? Then you will realize this VREF for the VDC. VREF for VDC, right? So VREF for the VDC. So you will compare with the actual VDC and then generate the error, give to the PI, and then that will generate one component here, right? So this is your DC loss component mainly, you can say. But if you will attach one extra PV extra boost converter there. So what you can do, you have two options. Use this current and voltage in MPPT algorithm and to generate duty cycle directly. One way is you generate duty cycle directly, or you can do this generate VDC ref, right? And then compare with your actual one, and then compare pass to the PI and generate this component assume as a duty cycle. So you have both way. So generate the duty cycle directly or pass with the error pass with the PI and generate the duty cycle after that PI. And then that PI generate the duty cycle, and then that duty cycle will be used for pulse generation for the DC-DC converter. So this way means only this portion will separate from here, right? That's why, nothing else. So in the two stage, but again the two stage have one merit, so you can use the smaller one, a smaller PV panel also you can use. Suppose your PV panel voltage is 100, so you can 100, so you can use one boost converter, and then you can lift your voltage and match your DC link voltage requirement, and then you can connect with the grid accordingly. So this type of things you will see. Similar type of control we can apply for the single phase also. This is for the three phase, right? But the same thing we can see for the single phase system also. In the single phase side, suppose this is a single phase system, but I will suggest in single phase system that much complex control is not necessary. That much complex control is okay with the three phase. When you are going for the three phase, means the phase unbalanced conditions, load unbalanced conditions. So this type of complexity you are going to face, right? Means your three phase loads, three phase load unbalanced, all these things are going to come. So that time it's okay. But if you are going with the single phase, so that time you can go with the other controls also, means the other smooth controllers also. The control techniques will be very similar, very same. So you can say, for example, here, so this is your load current, so you can pass with one filter and generate the fundamental component, right? So that fundamental component is this one. You can say ILP, this is your load current, right? Load current fundamental component. Then again, this is VDC, and then compare with the VDC ref, give to the error, and this is one component, and this is, you can say, this is the loss component, right? It's similar like the previous one, loss component for the DC link capacitors, that one. Similarly, this is the PV power. For PV power divided with the what, voltage, grid voltage magnitude, just like a previous one, PPV divided by 2 by 3 grid voltage magnitude. So you will see the grid current, sorry, PV current, equivalent PV current on the PCC. So like this, the same, these things are same like previous one. Just add both and subtract this one. So you can generate this IP. IP is what? Your grid current reference. The grid current reference magnitude. That's why. So this is grid current magnitude only. So you will multiply with the unit template, right? So you will generate UP. This is unit template, and just multiply with this magnitude, and then that will be the your grid current reference. Compare with the actual one and pass to the hysteresis and generate the pulse for that. So this type of things you will see. But the question is here, how we will filter out this one, this load current. So answer is definitely you can go the previous one also, but that one is too lengthy for the single phase. So I will suggest don't go for that. In single phase, you can use this the other filters also. For example, you can use the decoupled adaptive vectorial filter also. Through this way also you can get the very better performance, and this is little bit lighter in weight with respect to that one. So the if you will look on the basics of this decoupled adaptive vectorial filter DFV. So here what we are doing, so we will take the all those currents, right? Whatever current component or voltage components we will get, and then if this is three phase, then go for the clock transformation and convert into the V alpha and V beta. If this is three phase, if this is a single phase, then no need to convert, use this clock transformation. Just you have one single phase voltage, and then just give the 90-degree phase shift of that, and just assume this one is your alpha, this is, and the another one which is 90 degree apart from that, just assume that is your V beta in the single phase. Three phase, use clock transformation. Single phase, no need for clock transformation. Just go for the quadrature component of the, the actual voltage signal, like that. So you can generate the two V alpha, V beta, and like that. And after that, you will go through this filtration process. So what is this filtration process? This filtration process is based on this one, decoupling behaviors. So what we have done in this decoupling behaviors, we will take the differences and multiply with the one factors, and then multiply with omega. Omega here, this is a nominal frequency. This is not the actual grid frequency, right? Here we have used the grid nominal frequency. So that nominal frequency will use here for the filtering, and after that you will generate the V alpha dash and V beta dash. So this V alpha dash and V beta dash, whatever we will calculate, we will go for the phase shifting. So phase shifting is decoupling, so that if any unbalance you will see in between the two phases, for example voltage unbalance, right? So, but we are going to generate what, generate the balance current, balance grid voltage, sorry, balance grid current. So what we will do, we will do the cross coupling. So this is your cross coupling between what, alpha and beta, and alpha and alpha dash. What is alpha dash and beta dash, double dash? This is alpha double dash and this is alpha beta dash. Means plus 90-degree phase shift here and plus 90-degree phase shift here. So that you can say this is a double dash, this is double dash. So, and after that you will see this is a cross coupling. So cross coupling through this way or cross coupling through these calculations also you can go for. And after that, this way you can go, if this is three phase, then you can go for the inverse Clark transformation for that purpose. Or if it is a single phase, then directly you can use this one, B alpha triple dash. This is the your voltage direct, no need of any Clark transformation and all. So this is the behavior. This is the things here. For example, here, this is the block diagram of that. Three phase through the Clark transformation come with alpha beta, or you can go with this one, means just take the grid voltage here and 90-degree phase shift here, and go through these calculations, and then finally you will see this is your grid voltage, no need of any Clark transformation or all and like that. So in you will see one phase, one constant kf you will see here, kf. So how we will get the value of this k, this is also issue. So for that purpose we can go for the some stability analysis again. So here in this stability analysis, I'm not going to discuss all one by one, just you can go through the papers also. So this is very simple, nothing else. Just what I have done, I have just tried to formulate all equations, right? And after that, what I am trying to do, I am going to apply with the basic control algorithms. For example, this is the transfer function of that, right? So if we have, what is this? These are the integrators. So integrator we can replace to the 1 by s, right? Nothing else. This is 1 by s, we can say this is the integrator. If this is a 90-degree phase shift, so we can multiply with the -1. If this is omega, just multiply. So this way we can formulate one transfer function here, right? And s component will come because of these integrators, right? 1 by s terms. So finally, I can rewrite all those equations in this manner. So here you will see finally you will see one transfer function in between the input and output. These are the input component, these are the first phase of the output, and then again this output will link with this, and then you will see this is the final output of the DAV DF VF decoupled reductive vectorial filter. This is the output one, V alpha double triple dash, and this is the input V alpha, right? Similarly this one. So this is the output and input terms like that. So what we can do after that, we will go for the open loop transfer functions. We will try to find out the open loop transfer functions. So once you will get the open loop transfer function GS, so this is your GS. If we have this one, so we can calculate the open loop transfer functions. So this is your open loop transfer function. If you have this open loop transfer function, and in this transfer function you will see this is the constant kf. Kf is everywhere, right? Omega is frequency. So after that we can use the Routh-Hurwitz stability criteria. Open loop transfer function GS equal to 0, and after that if we have this GF equal to 0, so we can use the Routh-Hurwitz stability criteria. So this is the Routh-Hurwitz stability criteria, means the all the 2 power power 2 1 and 0 and like that. Means that here what we have done, I just put all those value means omega value I put it here, and then rewrite those equations. The equations will look like this one, and then you will see this one. So if you will go through that way, Routh-Hurwitz criteria, and what is the rule of the Routh-Hurwitz criteria? Choose the constant in such a way that this first column should, all the values of this constant or this column should be positive, right, or negative, whatever. A single notation should be, right. So if I'm going to choose positive, so if you will use the root orbis here, then you will see in this column so many k terms will come. So many k terms will come. So if so many k terms will come, then we can choose a value k so that all these values will positive. So how you will choose? So this is the way, through this way we can choose our k kf, sorry, the kf value we can choose in that manner, right? So this is the basics of the parameter selection. And once you will select those things, then you can go for the testing. Testing with respect to, again, we can go for the steady state analysis. Steady state means all the performance of all the controllers values with respect to what? The nonlinear load. So again, you can see this is your nonlinear load. So the nonlinearity load, TSD of this load is around 14%. You will see here grid voltage, sorry, grid current TSD is 4.3%, right? So you will see like this one. This is the behavior of that. Okay, so this is your grid current, and then this is the TSD of the load current, and like that. Okay, and also test in the solar radiance change conditions also. So this is for the your 1000 solar radiance, and then this one is for the 750 watt solar radiance. And both the conditions you will see MPPT is very close to that. Definitely the power has decreased also, but for example here the optimal power is around 3500 around. You will see that, and this is around 2600 something like that. But yes, in both the conditions you can see on the red side, this one, this side, this is your power, right? So here 3600 around you will see, and this is around 2600 around. So, but in both the conditions here, this green one, this is for on the optimal one, right? So this is on the 100%, close to 100% like that. Okay. Also, the tested under the different conditions, you can see the change in insulation, sudden load throw. Sudden load throw means your load gone, means load is zero. Then what will happen? Then when load gone means what? Entire power will go inside the grid, nothing else. Simple one. So you can go do like that. Decrease in PCC voltage, your grid voltage. PCC voltage means what? Grid voltage. If your grid voltage decreases, then what will happen? Definitely your grid current will increase. So you can see the waveform, because power is constant. Constant power is coming from the PV side. So this will increase. Similarly, if your this is increasing, means voltage sag and swell, like that. You can say that if sag swell is happening on the grid side, on the PCC, then how it is going to react, like that. These type of things you will see. And then this behavior. Similarly, on the day to night mode also behaviors you can see also here in the single phase also. It will night time start generating the reactive power and feeding in the grid. Also you can see that. Okay, so but this controller I will not suggest for the three phase. But three phase side, during the three phase the nonlinearity is high, right? The first of all thing, and then that time if you will go for the clock transformation, right? So here you will see the significant delay, and that delay will create a big issue. So that's why this controller I will not suggest for the third three-phase system. So this is good for the your single-phase system. But the three-phase system, the previous one is okay. But in single phase, this is good. This will work according to your choice. Because definitely here is some delay you will face. But through the decoupling, we have tried to sort out those delay issue, right? But for the three phase, this will not work efficiently. So we can go for the second one also. Okay, through this, I can conclude that here. So you can choose these two. But yes, if I will say this is not the end of the controllers, again, here is some in chances of improvement. You can use this, sorry, you can go for this, go for with a new controllers, and then you can improve it further, right? Because again, you can see here the TSD is not zero. Definitely TSD, some amount of TSD is here. And also if the nonlinearity of the load is going to increase, suppose here the nonlinearity, what I will consider that is around 27%, 29%, 30% around load TSD. If the load TSD is further more, so that time what is the impact of that? So on those directions you can reinvestigate. So how you can do that, right? So these are the works are still list, so where you can think. And this controller, what I have discussed here, this is not only dedicated for the solar. Same controller will work for the wind also. If you are working for the wind, only the on the place of solar, your wind output terminal will attach. Wind output terminal, for example, your wind is based on the PMSM. So what you will do? PMSM, wind turbine, a PMSM machine, and after that the two converters, and then second converter output terminal you will attach on the PCC. Sorry, not PCC. I mean DC link. That's it. And rest all the control behaviors will same, nothing else. So you can use for that purpose also. For example, here, so what we have PV power, on the place of PV power, you will write wind power. And then in the connection side, I will say in this connection, on the place of this DC link, sorry, this DC boost converter and then panel, you will remove only the output terminal of the wind converter. I'm not talking about the machine, not direct machine. For example, PMSM, type 4 PV wind generator. So the second converter output terminal DC component you will attach here. That's it. And rest all the controllers will be same and it will work like that. Okay, so you can apply for use for that purpose also. If you have multiple sources also, for example, if you have the I will say a small hydro, right? So you that will attach here. You can attach that one here, small hydro that will generate the AC power directly, so you can attach on the PCC directly, right? And then that time that that will consider also in the grid as a one component. One component means this one, the negative component. So that component will also minus here. That's it, nothing else. Minus because this is the generated power. So whatever the generated power is that just divide to the VM means the grid voltage magnitude and just minus here, and like that you can use for that one also means through this controller just add on those source components and you can remodify for the different combinations of the sources. Okay, so that's it. If you have any questions, I am happy to answer. Thank you.
Thank you, Dr. Nishant. Now I would like to request to the participant if they have any question, they may ask directly to the speaker. So, Dr. Nishant, I have like one question. You will explain it a little bit more. Like in the night times, you have discussed about that the harmonics component will be created by the PV system.
Converter.
Yeah.
uh, yeah. So actually, not through the PV system, just only the this. For example, in the night time, this converter and then this capacitor. That's it. This capacitor and this converter. This will generate your those current, those nonlinear currents only. This PV panel and this diode, and then suppose if you have the DC-DC converter, so that will not in the operation. Just like a D-Statecom. If you will look on the D-Statecom structure, so what is that? That is only this one, means the filter interfacing inductor and this BSE, right? So
Okay.
this is D-Statecom. If you will remove the panel here, it will look like a D-Statecom, right?
Okay.
So just simply in the night time, it will act like a D-Statecom or a Statcom also. If you will remove this load and just you will assume this one is your grid and this is your connections, means converter and then this link. So this actually what this converter is going to generate. This converter will generate according to your reference. What reference? Grid current reference. What current reference you are going to give that one. That's it. So if you will in the night time when the PV power is zero, so that time only you will see on the component side only harmonic components are going to come in the picture for this converter. Rest all those fundamental components is going to come through this way, grid side. So if you have the references like that, if you will plot the reference curve in the night time, or you can take the term zero in this structure here, if you will take this zero and then you will plot this in the night time, then you will see this is just only harmonics component. So that's why this converter is uh, trying to generate that signals accordingly.
Okay.
This is not only for the nonlinear side. Also, we can generate the reactive power also. What we will do, just we will take the grid current, grid voltage, right? And then we will generate intentionally we will generate one signal which which is 90-degree phase shift with the grid voltage, 90 degree. So the 90-degree phase shift means what? That is that is reactive. That's it. And the magnitude we can set accordingly, what magnitude we want to face, or what amount of reactive power we are going to supply inside the grid. So this converter will start generating that type of current. So current reference modulation is important here.
Okay. One another question is like nowadays we are moving towards the DC sources like either PV or other different other types of generating stations, especially for the renewable energy based. And the another load is like also hiking, like with the like EV systems are there, and all are they are feeding just the active power or either consuming the active power. So
Right.
does it affect the
Yeah, yeah,
system?
yeah. That will attach here on the DC tie line mainly. If you were if you were thinking for DC loads, so that only you will take the DC power, active power, and all. So it means that you will attach directly your all DC loads here on the DC link, DC tie line here, right? So if this is the DC tie line, so if you will attach your DC loads here, so that time you just in this control one extra term you will add here. What term you will add means the this time your this PPV is not VPV here this time. Sorry, not VPV, means multiplication of VPV into IPV. This is PPV. So that time this PPV will change. PPV minus DC loads, that is the power. Only one term you will change here in this controller. If you will attach any DC loads, so just change here PV power minus those load in bracket. This is the PV power. So because the what amount of power you are going to feed, that is going to decrease, right? Simple. So that time this PV power become not PV power. That time that will become the PV power minus all those DC loads. So you can attach. Sometime you will see the someone going to attach one battery bank also here. Battery bank with the DC-DC bidirectional DC-DC converters, or direct PV, sorry, but EV charging. So that term, then you just you will change one term, and then it will look like that.
Yeah. You have also mentioned about the like on-grid systems, but um, in the remote India, we don't have the grid availability in the
Yes,
24 into
eh,
7.
agree. That time this control, what control I discussed today, it will not work. Whenever your grid will zero, whenever your grid will zero, this control will not work. So for that purpose, in general, you will see. So this is your current control mainly. So for that purpose, we follow the second control, that is your voltage control. Once your grid current will go, so that time we will try to generate virtual grid by using the voltage control. So that time we will choose our own frequency, and then we will generate the grid current accordingly. So that time this will not work. Why? Because that time this voltage term will zero. These are become zero. UA, UAB, UBC. So these become zero. So if this becomes zero, so reference current becomes zero. So on that time, what we will do, we will generate this UA, UB, UC intentionally at
Okay.
base at 50 hertz, right? And here the matching of sequence matching is not important because we don't have grid. So we can generate any sequence. Means this is on zero, this is 120 degree, and this is on 240 degree, and then we can operate the same system like that. That is the voltage control mode.
Okay. Thank you very much.
On behalf of the Albag Education Institute, I would like to pay a sincere gratitude to our today's speaker, Dr. Nishant Kumar, for his time and for enlightening us and providing an in-depth knowledge of the topic, that is how one can make use of AI-based techniques to design the control systems for solar applications. So thank you very much, sir, for your time, and thank you very much for enlightening us with with this topic, so that later we can utilize this knowledge and to find out the research gaps, and surely we can find innovative solutions in the same field. Thank you very much. And as a token of respect, this is our e-memento from our side for being honorable speaker in today's session. Thank you very much.
Thank you. Thank you.